Welcome to this video. This video is part 1 of this building recommender system using GNN with PyTorch series. This one is mostly going to cover introduction to GNN, some intuitions, and also cover how to do some of the graph manipulation for data preprocessing. So let's get started. What is graph neural network? If you clicked on this video, you might already know some, or you're at least curious about it. Graph neural network in simple term is basically meaning we're going to process the input data in the form of graph. So we pre-process input data in a graph form, and then we feed the model and we design a model to be able to handle this graph type of input. And GNN has many applications. If you look at modern society, we have social media, which is essentially social network. We have many purchase interactions, that's essentially user item interactions that can be modeled and applied to recommendation system. We also have knowledge graph, for example, for science research or for movies, you have all these knowledge graphs. That's essentially graph neural network. So graph neural network has a lot of applications. One of the common comparison that people drew similarity from is convolutional neural network. So a lot of people say these two are very similar. Let's revisit what CNN look like. So CNN, convolutional graph neural network, is commonly used to process images. If you look at image, it's essentially input as pixel grid. So for example, here, right, you have a 4x4 picture. So it's a very low definition picture. And you have this green box that slide over your picture pixel grid to extract and to get a more condensed information. So if you look at this, right, you have an input of 4x4 pixel grid, and when you do this box sliding, you take either the max or the average of values within each box, then you're getting a 2x2 matrix. And that basically gives you a more condensed information, or it's called higher level information of your image. So now let's look at graph. How do we do that? We can't have a box moving if graph doesn't look as nicely organized as kind of like a square grid, right? So where is this conclusion of similarity come from, and how do we understand it? So if you look at CNN, instead of understanding each small grid within your sliding box, let's just say here like a 3x3, you look at it as I have a central node here, and whatever I extract from this box is essentially given the central node and its 8 neighbors that surrounding it, sometimes including self. What is the aggregated information of this kind of a cluster, right? And then you move on to the sliding to the right. So if you look at in that aspect, then it's essentially a node with aggregate information coming from all of its neighbor nodes, and that is how you extract information. And if you apply that to graph, then you will get something like this. You will have a target node I, and then say look at one hop or layer 1, then you have 3 neighbors, and then you have at the next layer or next hop, then you add 4 more neighbors. So node I's embedding is basically aggregated from its 3 neighbors from the first layer, and then the 4 neighbors of the next layer aggregated kind of recursively to give you the embedding of node I. So that's why people say graph neural network and CNN are similar. So given that, how do we design the model, a generalized model for graph neural network? So given this input graph, right? So we have a target node A. So if you do this kind of finding neighbors and aggregating, and you expand that, then you have this computational graph look like this. So given node A's embedding at layer 2, it will basically look at all 3 of its neighbors, B, C, and D, and what's their embedding, and it will basically aggregate them in this gray box. And for each of the node B, C, D, it will do the same for their neighbors to get their embedding at layer 1. And at layer 0, at this point, they don't have any neighbors because it's a layer 0. So what often happens is either you use just a feature vector of node, each of the node, or you have a randomly initialized embedding vector, and then that is the vector you will learn through training, which becomes the representation of your node. So this is the GNN computational graph of how embedding are computed. So let's look at what's inside that gray box earlier. So it basically consists of 2 parts. One is this message transformation, and the other part is called aggregation. So message transformation basically means given embedding at all my neighbors, I'm going to do some transformation, and I'm going to aggregate them, and then output that to as the new embedding at this current layer of this yellow node. So this is all nice and neat, but what's the mathematical formula of this? So the following section is going to be very math heavy. So just a quick heads up. So ready? All right. So this is the general formula of message and aggregation of how we compute embedding. So let's go over each of the notations so you don't get confused. So K here refers to which layer you're at, and sometimes you see big K, which refers to the total number of layers. And here I and J, or I just means this is the target node I'm trying to compute its embedding. And J means all of its neighbors. You can also see from this notation, right, that J belongs to all of the neighbors of I. And then X here refers to the embedding. That's why it's bold. It's a vector. And you will sometimes see the notation is using H or E, but it essentially refers to embedding for each node. Here you have sigma, which is a nonlinear function like ReLU, sigmoid. This is basically after you aggregate, you pass through a nonlinear function. And aggregate here refers to permutable aggregation. So it basically means the order of whichever item comes in doesn't matter. So the aggregation functions that fit that criteria are like sum, min, max. And here you have a normalization term, which means if this message from my neighbor xj has a lot of neighbors, then I want to normalize the proportion to the neighbor count of x. And that's why sometimes it's used I divided by the neighbor count of j as a normalization term. So if you understand it intuitively, it basically means if node j has a lot of neighbors, then the message that node I is getting should be weaker, right? So this is similar to I would say similar to the page rank idea, the reverse page rank idea, I guess, where if node I is only a small part of whoever node J is communicating with, then it should only get a small share of that message, the weight of that message. So that's what that is. And let's break down this formula into what we mentioned earlier, the message transformation and aggregation. So it's simply the neighbor times a weight. This is just a linear transformation normalized by the neighbor of this node J. And then aggregation is just this, right? Aggregation and then pass through a nonlinear function. So that's this. So LightGCN is the model that we will use for this recommender system example. It's basically an improved version of GCN. So if you look at the formula here of how embedding is calculated, like I mentioned earlier, it will sometimes use H or E. So here it uses E as the embedding notation, right? And then here it, instead of dividing by just whatever the neighbor's neighbor count, this is called a symmetric normalization term. So it's just a fancier way to normalize the message coming from neighbor that's proportional to not only the neighbor's neighbor count, but also this target node's neighbor count. So EU means for user, the user embedding, EI means item embedding, but these two formula are basically the same except for, you know, U and I basically flipped. So given the embedding at each layer, this is how you compute it. How do we get the final embedding that we use for prediction? So this is what this formula is for. So we basically say we want to multiply, just be aware all these are element-wise operation. So the alpha here is a hyperparameter, but if you actually read the LightGCN paper, the recommended number is just to use 1 divided by the number of layers. So it looks like a sum, but essentially if you consider this term being the number of layers, then it's basically getting an average. So it basically says, give me all the layers for this user as final embedding. It basically says for all of the embeddings at different all its layers, I just want to get an element-wise average, and that will be my final embedding. So if I have basically so if its embedding is a vector of size of 10, then how you compute the value, the final value as size of a position 1 is, say, for all the embeddings from 0 to k at position 1, just add them together, divide by the number of layers, and that will be my embedding, the final embeddings value at position 1. So this is for item embedding, it's exactly the same. And how we make prediction is simply a dot product, or you can take the embedding and do some other tasks, or even like transfer learning if you like. But the basic one is just a dot product between user and item to determine similarity. So that's that. So this is the LightGCN model matrix form equation. Why do we care? I know many people hate linear algebra, including me. I think a big reason is because it was taught out of context. So now when you need it to understand deep learning, and a lot of those knowledges are gone. But it's actually very, very important to understand those, because for machine to compute all the deep learning, it's easier to use matrix manipulation, and that's why there's this matrix form equation as well. That is actually what, under the hood, what code is implementing. So let's look at it. So this is similar. So this EK plus 1 and this whatever this term and then EK is exactly the same as here, except the one except for A here means adjacency matrix. So, but it's basically the same. So A means adjacency matrix, and then D here is a diagonal matrix that has information of node degree or the number of neighbors of each node. So if you do diagonal matrix look like this, right? Everything else is 0 except for the diagonal. If you do this diagonal matrix and then add this inverse square root, and then multiply by adjacency matrix. Imagine adjacency matrix is a m times m matrix, and this is m times m as well, right? The diagonal matrix. Then essentially you're multiplying this one of these terms, the 1 divided by square root number of nodes of I, to every single item or every single entry of matrix A. And then you do it again with this D. I think it's missing a notation. But if you do it again with U, then you're getting this full, it's called symmetric norm. So what this is doing here is essentially what this is doing, but in a form of matrix. Right here is we're just looking at mathematically what a single like a vector means, but then here saying, okay, if E is a matrix of all of the embeddings of all the users or all the items, then this is how you would compute it. And then the second equation is straightforward. It's basically mapped to here. You just add this hyperparameter term, or sometimes 1 divided by number of layers. So A is, so this alpha is applied here. And A tilde, this is called symmetrical normalized matrix. This is basically doing this, but then because this is just for one node, right? And we need to apply this based on the number of neighbors on the entire embedding. So that's why we have this A tilde. So I guess in summary, what this is doing is exactly what this page is doing, except for this is written in a way that we're looking at embedding at each node. And here is written in a way where we're looking at embedding of all the node. So EU here is a vector, and then E, the big E here is a matrix. So that's the only difference. And the benefit, like I mentioned at the beginning, is that for computer, actually it's easier to compute using matrix manipulation. So the other concept that I'd like to cover is graph representation. So like I mentioned at the beginning of the video, a big part of graph neural network is pre-processing your data in the form of graph representation, so your model can take it in as graphs. So adjacency matrix is a very popular way to represent graph, and I think many of you already know adjacency matrix. So essentially, if you look at here, node 1 and node 4 connected, then the way you look at it in the matrix is at first row, column 4 means node 1, and fourth column, node 1 and node 4 are connected. And similarly, node 1 and node 2 are connected. And how do you know that? The second row and first column means node 1 and node 2 are connected. And notice this is undirected graph. So it has a nature where it's basically diagonally symmetric, right? So you have one here, one here, one here. So it's diagonally symmetric. You also have directed graph, so the same rule for adjacency matrix still applies. One important nature of adjacency matrix is that for the row index and the column index, they're supposed to mean the same thing. So for example here, row 2 it refers to the second node, and column 2 is supposed to refer to the second node as well. And you'll understand why this is very important. This concept is very important. The next thing is the other way to represent graph is called COO, stands for coordinate format. It's basically a good way to store a very sparse matrix in a very space efficient way. So this is pretty straightforward. The first row, right, so here you have 3 means a row 3, and then column 4, and then that gives you the value 5. So it basically stores your graph, because it's so sparse, it stores your graph in the form of edge pair, but it's actually a 3 list, right? So if one list, the first 2 lists are basically edge pair, and then the third list is the value of each edge pair and a corresponding order. So that's why sometimes you will see not just row or column being referred to as these two rows. Sometimes it's also called source and destination. You'll see those notations as well. And then the other concept is the first 2 list sometimes is called sometimes called edge index. So the edge index is actually the input to a lot of graph neural network model. So this one, I think it's a little bit counterintuitive in terms of sparse and dense. If you look at just the words itself, right, you would imagine dense means you're storing a matrix in a more dense form, and sparse means you're storing in a more sparse form. But it actually means the other way around. It actually means for sparse, it means my matrix is very sparse, so please store it in a more space efficient way, in this case in a COO format. And then dense means I don't really care to be space efficient, so just store it in a list of lists, which is adjacency matrix, or just a list of lists. So that's that. The other very important concept is bipartite graphs, and the reason is that a lot of recommendation systems are based off this, right? Because you have user on the left side, item on the right side, right? Users. So the definition of bipartite graph is there are 2 types of nodes, and they only interact with each other, but the same type of node don't interact. So user A and B don't interact, but user A do interact with all the item nodes. So that's why it's called bipartite, because you kind of like divide it by 2 groups, right? Left group is user, right group is item, and they interact with each other, but within each group they don't interact. So how do you get adjacency matrix from this bipartite graph? So as I mentioned earlier, if you look at adjacency matrix, right, there's an assumption that, or by definition, we're saying that the column index and the row index is supposed to be referring to the same node, but now we have two types of nodes. So how do we do that? So the way to do it is you start from this thing called interaction matrix, where the row index represents one type of node, and the column index represents the other type of node. And then you do this conversion as following to convert your interaction matrix into adjacency matrix. So you have basically, you put the interaction matrix on the top right, and then on the lower left with the transpose, and then all the other empty space you fill with zeros. This is not just one zero, this is multiple zeros. That's why it's on bold. So if you have an input of interaction matrix of m times n, then your adjacency matrix will actually be m plus n times m plus n. So I'll show you an example of what it looks like. So let's go to the notebook. So here's the notebook. So here I'm using PyG. So if you're having trouble installing PyG, and if you're using MacBook, I have a video on how to install that. So I'll link that in the comment section and description. So that's import all the required modules. And this is an example that I want to give for this kind of small hands-on exercise. So we have this 3 times 4 interaction matrix. So we have U1, U2, U3, I1, I2, I3, I4. And so U1 interacts with I3, I4, U2 interact with I1, I3, U3 interact with I1, right? So this is an interaction matrix. So let's write it as NumPy and print it out. So it looks exactly like what we write. And here we basically say I want to use this Sparse module, which is imported from SciPy, and then which is imported from SciPy, and then I want to convert this. I call it RMAT, right? R, remember in the slides, R is stands for interaction. So I want to convert this interaction matrix into because it's list of lists, right? It's a more dense form. I want to be more space efficient, so I want to convert it to COO format. So let's see what it looks like. So here you're basically getting edge pairs with the values, and then from here you can actually retrieve the rows. So if you look at the slides, the rows and columns, so you can actually retrieve those by doing .row and .column, and that gives you the edge index. And then we do the toDens to convert it back to the list of list format to kind of have a nice visualization. And you can also do the same thing with PyTorch. So you just need to take the edge index, and then you convert it to tensor, and it looks like this, basically the same as above. And then you say I want to store it as a sparse tensor. It basically does the same thing as I want to store it as a sparse COO format. So if you do it and you print it out, it will actually does just that. It actually shows you the density, which is quite nice. And you can choose, and you can call toDens to convert it to the list of list format, so it has a nice visualization, right? So this is exactly the same as this interaction matrix. So 0, 0, 1, 1, 1, 0, 1, 0, right? So here 0, 0, 1, 1, 1, 0, 1, 0. So this the other important part I mentioned in the slides is for bipartite graph, the interaction matrix is not the same as adjacency matrix, because in adjacency matrix, we have this assumption that the row ID and column ID, or sorry, the row index and column index are supposed to be referring to the same node. So we're doing this this conversion to convert from interaction matrix to adjacency matrix, right? Basically, we're doing what we mentioned right here. So I have these two helper functions to allow these two conversion, and these two are very helpful in actually writing the implementation, because what happened is the model takes the adjacency matrix, but then when you do the calculate all the recalls or NDCG or all those evaluation metrics, it's actually more neat to have the edge index stored using this interaction matrix format like this. So you can have a very nice first row is all user ID and second row is all item ID, that format. So that's why I have these two really convenient helper method. So for this one, I'm converting the interaction matrix edge index to adjacency matrix. So the first step is saying, give me the the row size and column size, or number of item in the recommender system context. And then I just fill them up based on my input edge index. And then here I'm doing this the conversion right here. That gives me the adjacency matrix, and then I convert that to the sparse COO format, and I call dot indexes to get the edge index from adjacency matrix. And here I'm just doing the reverse of what I'm doing above, right? You have an input that is adjacency matrix. I want to save it in a sparse format, COO format, and then I can call toDens, so it gives me the list of list, and that way I can basically just crop this top right to get my interaction matrix, and that cropping is basically done right here. And once I have that interaction matrix, then I just do toSparse and indexes to convert it back to the edge index. So a quick demo here. So my input is interaction matrix, and row size is 3, column is 4, right? Based on this, right? So here's what it looks like. So you have this nice edge index after you convert it to adjacency matrix. You can kind of see it's sort of symmetric from like left if you do like draw a line in the middle. Not exactly symmetric, but all the pairs that exist on the left you can also find on the right. So that's the nature of this. And then you convert it to COO, and then you say toDens, and then you can kind of see it's in this format. So you can see like it's 3 times 4, and then here it's a transposed 3 times 4 right here, and all the other space are filled is 0. So let's convert it back and then see what it looks like. So it looks like the original interaction matrix, right? 0, 0, 1, 1, 1, 0, 1, 0. And then if you scroll up, right, 0, 0, 1, 1, 1, 0, 1, 0. So that's it. So that's it for this video. Thanks for watching. This is just the part 1. Part 2 or future videos will be more hands-on on how to implement. So thanks for watching, and if you like this video, please don't forget to click subscribe and like. That will motivate me to make more videos like this. Thanks for watching. I'll see you in the next video.